Okay, so far we've been talking about how we can find equilibrium for systems of differential equations, and then how we can find solutions at least in the phase plane. So let's combine both of those ideas in these two examples. So we'll take a look at first this example where we have dx dt equals 6x and dy dt is equal to 3y. And so let's first find the equilibrium for that system. So we need to identify where dx dt and dy dt are simultaneously zero. So starting with the x dt, that's a pretty simple equation to solve. The only way that is zero is if x is zero. And similarly, from the second dy dt equation, we see that y has to be zero. So we have only one equilibrium at the origin, the point 0, 0. Next, we can set up the phase plane equation by taking the y dt on top, which is 3y, and dividing that by dx dt on the bottom, which is 6x. So our phase plane equation is 3y over 6x, which we can reduce to y over 2x. And again, we have a separable differential equation, so we can separate that differential equation. And so if we bring the y to the other side, we get 1 over y dy, and we bring the dx to the other side, we get 1 over 2x dx. Integrate both sides, so we get a natural log of the absolute value of y is equal to 1/2 times the natural log of the absolute value of x plus c. We can solve for y now. If we want to give an explicit solution, we can exponentiate both sides. So on the left side, we would have the absolute value of y, and simplifying the right side, we would get the absolute value of x to the 1/2 power. So in other words, we would get the square root of the absolute value of x, and we would multiply that by e to the c, which is just some other arbitrary constant c. And so here we don't need any of the absolute values. We get y is equal to c times the square root of x as our solution. And so notice here we got rid of all of these absolute values, and we can do that because first of all, if I'm taking the square root of x, we assume that it has to be positive, so we don't need an absolute value in here. And depending on the sign of y, that would affect just this arbitrary constant in front of here. So we could write out this solution as y is equal to c times the square root of x. And let me just say that this is kind of a special example because it's really just two totally independent differential equations. This doesn't depend on y, and the equation for dy dt doesn't depend on x. And so we could actually have just solved this system directly by integrating each of those equations. And so, for example, integrating the top equation would give me that x is equal to c times e to the 6t. And solving that for y would give me y is equal some other constant, so I'll call that c2, e to the 3t. And so that's why we can see that y is actually equal to the square root of x, and they might differ by some constant multiple. But this example is special in that case, in that we really had two separate differential equations. So for this next example, we certainly couldn't do that since these equations are intertwined. The equation for dx dt depends on y, and the equation for dy dt depends on x. So let's take a look at this example. First, we want to find the equilibrium. So we want to find, for example, when is dy dt equal to 0? Well, that very clearly is when x is equal to 0. That has no effect on the top equation. So the top equation is going to equal 0 only if y is equal to 1. So we have one equilibrium when x is 0 and y is 1. So there's our equilibrium. Next, we set up the phase plane equation. So we want to find an equation for dy dx that we get by taking the minus 4x on top, dy dt on top, and then we divide by the x dt on the bottom. And so we can simplify this before we integrate it. For example, we can reduce this to minus x over 1 minus y. We don't need to do that, but maybe that'll make it simpler in the end. So again, we have a separable differential equation. So we're going to separate our x's and our y's. I multiply both sides of the equation by 1 minus y to get the y's on the left side, and I multiply both sides by dx to get the x on the right side. Then we integrate both sides, so I get y minus 1/2 y squared is equal to minus x squared over 2, and we've got our arbitrary constant. And so we can bring all of our terms to the left side and write this as y minus 1/2 y squared plus x squared over 2 equals some arbitrary constant c. So that would be our solution to the phase plane equation. And so here we actually don't know how x depends on t, how y depends on t, but we did find how x and y depend on each other. And so in this case, I'll stop here because here we have an implicit solution and we can't actually solve uniquely for y. So at best, we can give an implicit solution to that phase plane equation.